Thank you so much, everybody. It's a real pleasure to be here. I was actually an honours student here at Mount Stromlo 15 years ago, so it's always lovely to come back. So thank you to the organisers for inviting me. As was pointed out this morning, we didn't have a strict planet formation lecture, so we're skipping straight from disks do stuff, a miracle happens, exoplanets are there and available to be detected. And I'm going to tell you how we detect. Just assume that a miracle happens and exoplanets get made. Okay. Is it supposed to do something? Bingo. It's got lights.
Is it not working?
Nothing's working, actually.
Oh no.
I broke it already. I'm sorry.
Wait, there it is. Yeah, so just left and right.
Yeah. Okay. All right. So just briefly, one of the things I wanted to talk about was the fact that we've actually only been able to detect exoplanets for the last 25, 30 years. But that doesn't mean that the idea of exoplanets wasn't around for thousands of years before that. The Greek philosophers were talking about the idea that there could be another Earth out there, completely hypothetically, kind of the way we talk about multiverses now, like, isn't this a neat idea? Let's just gas that about the prospect that there might be another Earth out there. But the idea had been around for a long time. I specifically wanted to name check Giordano Bruno, who was a philosopher in the Renaissance, because he was one of the first to really articulate the problem. So I'll just read his quote. There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system. This is 400 years ago, so cut him some slack. We see only the suns because they're the largest bodies and are luminous, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no worse and no less inhabited than our Earth. So maybe he was stretching a bit with the last one, but his point is valid, which is that they're really hard to find. The Renaissance actually turns out not to have been a great time to be talking about exoplanets, and he was actually arrested by the Roman Inquisition and burned at the stake in part because he claimed this existence of the plurality. I'm too jet lagged for L's and R's. So because, you know, the church was a big deal in Italy 400 years ago, and saying that, I mean, he said a bunch of other things that weren't wise to say as well, but saying that there were exoplanets got him burned at the stake. But I really like his final words, which are just pretty baller. Perchance you who pronounce my sentence are in greater fear than I who receive it. And 400 years later, turns out he was right. There are planets everywhere. This is just a visual representation of the difficulty he was talking about. And this is the fact that even the biggest planets in our solar system, Jupiter and Saturn, the sun is 10 times bigger, 1,000 times more massive, and 1 billion times more luminous. So trying to find a planet like Jupiter next to the sun is like trying to find a firefly next to a spotlight. And I like this picture because the story that's attached to it is the National Geographic guys who are trying to take this picture really liked this analogy, that it's like a firefly next to the spotlight. That's really cool. That's a good visual to get across. And then they were trying, and they were saying to the astronomer, who was Sarah Seeger, we can't get a picture of a firefly next to the spotlight. She's like, that's it. You understand. So they actually photoshopped the firefly because you can't actually take a picture of a firefly next to a spotlight. Finding planets is hard, guys. All right, but we have had some success now, and I just wanted to walk you through. This is just a visualization of the time going along and the planets that we've found. Okay, there is groovy music, but I didn't plug it in. So what's being plotted here is the period of the exoplanet and the mass on the y-axis. And what you're seeing with time is the exoplanets that are getting found filling in this space. So Earth would be down here somewhere. So 365 days, 300th the mass of Jupiter, down there. So we haven't found Earth's twin yet. Spoiler, I just give it right up the front of the lecture, we haven't found Earth's twin yet. But what you can see is that we've used a whole bunch of different techniques to find exoplanets, and that those techniques are sensitive to different types of planets. Now, I only have 40 minutes, so I'm not going to be able to give you an in-depth crash course in every single detection technique. So like Mike was saying this morning, these are multiple people's PhDs at each step. But what I want you to take away is the basics of the major techniques, how they work, what they're sensitive to in terms of parameter space, and maybe a little bit about where their future lies. So here's a breakdown. We've got 3,500 confirmed exoplanets now. And here is a breakdown of how they've been found, the discovery technique that was used to find them. And you can see, as I said, there's a whole bunch. But you can also see there are some methods that have found much, much larger amounts than others. So those are the 4 that I'm going to concentrate on today. We'll go into a little bit of detail about these. And as I said, not much because we don't have a lot of time. But these are the 4 that have been the major contributors to the exoplanets that we've found so far. The rest I will touch on very lightly, 1 slide each at the end, just so you get a flavor. Okay, so the first one we're going to talk about is the transit method. So this is the sun. Does anybody know what that is?
Yes.
It's Mercury. It's Mercury. Mercury blocks 0.002% of the light that comes out of the sun. So 20 photons out of every million photons that come out of the sun get blocked when Mercury goes in front, when Mercury transits. Now that's not a lot of light. That's a very, very difficult detection to make. You have to have extremely good photometry to measure a change in 20 parts per million.
Do you happen to know how often Mercury transits? It's not every often.
No, it's not. See, I know this answer for Venus because it's like pairs every 8 years apart, every 80 years. But I don't know for Mercury actually.
It would be more often, more frequent. It's every 5 to 6 years.
Okay, because the period's like 83 days, 87. So Earth blocks 0.01% of light, so about 100 parts per million. So that's still pretty difficult, but at least we're increasing. But luckily, Earth's not the biggest thing in the solar system. Jupiter comes along, and if you were an alien civilization very far away and looking back towards the sun, Jupiter would block 1% of the light. So 1% photometry is starting to be achievable from, say, the ground. But really only once we had CCDs, once we were able to get precise photometry from the ground were we able to see these things. And then I was finally able, after like 10 years, to update the slide this year. If the moon transits, it blocks 100% of the light. All right, so there's pros and cons with the transit method. One of the pros is that it's one of the only techniques that gives you the size of the planet. That's the radius of the planet. And it only gives you the size of the planet as well as you know the size of the star. So that's an important caveat that we'll touch on a little bit more. Some of the other techniques, which I'll talk on, give you the mass of the planet. So if you can use both techniques, the transit technique and one of the other techniques that gives you mass, now you have a size and you have a radius and a mass. So now you can start to talk about bulk density. Is it a rocky planet? Is it an icy planet? Is it a gas giant? That kind of thing. So this is one of the few methods that gets you there to that answer of whether something's icy or rocky. Another exciting thing about transiting planets is that you can study their atmospheres. So as Jupiter, for instance, goes in front of the sun, starlight streams through the upper atmosphere of Jupiter, and if there are molecules in there that are absorbing some of the light, that planetary spectrum gets imprinted on the stellar spectrum. So you take spectra of the star without the planet in front, and then a spectrum of the star with the planet in front, and then you do what they tell you never to do, take the difference of 2 really big numbers, you get a small number, and then learn something about the atmosphere of the planet. So that's one of the ways that you can probe atmospheres is with transiting planets. There are problems with transiting planets though, and one is this geometric probability that I alluded to. So if you're an alien civilization very far away from the sun looking back, most of the stars in the sky wouldn't see Earth transit. It's not lined up right. So there's a band around the sky of stars that would see Earth transit. And in fact, the probability of a planet transit goes as the size of the star over the semi-major axis of the orbit, which is to say big stars are good and small orbits are good. But something like the Earth is not great. It's very far out. So Earth only has a 0.5% chance of transiting for a random star in the sky. So that means you have to look at 200 Earths to see the one that transits. So you have to look at a lot of stars in order to find the planets. Most planets don't transit, I guess is the takeaway, right? So that's the problem with the technique. You really have to search for harder and further to find planets. Another problem with the technique, which is a problem with all of the planet detection techniques, is false positives. So this here, I didn't really talk about, it's a sunspot. It's actually bigger than the Earth. Earth fits inside the sunspot. And the sunspots are changing the brightness of the star with time. So if you're relying on a technique that's measuring the brightness of the star with time and waiting for dips to happen, if that brightness is doing other things because of star spots or activity or anything that's happening, it becomes that much more difficult to pull out a signal like the Earth. So stars do stuff is one of the annoying things for transits. Okay, so here's some light curves. So this is measuring the brightness of the star with time. This is the star Coro 1. Corot was a French spacecraft. Not that I just put it in because it's French or anything. No, very important. So here's a light curve of the star with time. And what you see are these dips that happen every 1.5 days. And what that corresponds to is the period of the planet. So every 1.5 days, this very short period planet. We just talked about Mercury having a period of 80 days. This planet has a period of only 1.5 days. And one of the exciting things about this, like the first decade or two of exoplanet detection was discovering this whole population of planets that were on orbits of only 1 or 2 or 3 days, which had been predicted in 1950 by Otto Struve. But, you know, this whole idea of hot Jupiters, these giant planets really close in, was incredibly exciting when we finally detected it. So that's what Corot 1b is. It's a hot Jupiter. It's a Jupiter-sized planet in a 1.5 day orbit around a star. So the distance between the transits tells you the year of that planet. So Earth would have dips every 365 days. So this is a different planet, KOI 451b. You might recognize this phone number just last week, like 3 days ago. This was the system that was announced to have 8 planets in it. So it's now the tiebreaker record, or tie holder with the solar system. The solar system has 8 planets. So this is the first exoplanet system that was found that had the same number of planets as the solar system. So this is the inner planet from the system. And what I wanted to show was that the depth of the dip tells you the size of the planet. The depth is there should be a square in there. This should all be square. RP over R star squared. I was doing that on the plane. Sorry? Oh, yes?
Sorry, I was just wondering, is it possible there are more planets that we just can't see?
Oh yeah, there are definitely more. We don't see most of them.
So, in the system we've seen 8.
Oh, in the system we've seen 8, yes. So the 8 that we have found are all interior to the orbit of Earth. So this system has 8 planets up to, I think the outermost period is 330 days and Earth is 360. So there could very well be things past there. The problem is the Kepler data. So Kepler is a spacecraft that observed this star, only went for 4 years. The observation base only goes for 4 years. And you need several transits in order to get this period. If you see one event, it's really difficult to know what the period is. If you see 2, you may, if you're a gambling person, you can be like, to the same planet, this is the period, but maybe it's 2 different size planets like Earth and Venus just happen to, transit 40 days apart. So you really want to see 3. But that means in the Kepler data, which is 4 years long, we're not sensitive to things much longer than the period of Earth. So if there are bigger things further out in that system, we weren't sensitive to them. We didn't have enough data to find them. But there absolutely could be. 8, there's no reason why 8 is a special number. It's just exciting because 8 was the highest number we knew so far. And it's like, yeah, another one with 8. Yay.
Just have you quantified the number of Jupiters that passed only once that a big dip, but it didn't happen again because the period is too long?
Yes, so it hasn't been quantified. Several different people have done different types of searches for that kind of thing. So early in the Kepler project, we didn't have all the code working yet, and Jason Rowe, who was at that time a lowly postdoc, would just sit there and look at all of the light curves by eye and find all the events. So that was in the first 3 months of Kepler data. There have been several other people, I think Saul Rappaport is one, who have done searches for events that only happened once or twice. And Dan Foreman-Mackey, that's right. So basically, almost all of the transit detection codes that people use look for multiple signals. So you need some other kind of code to go and find a single signal that you then characterize in more detail.
Wouldn't be a sort of different timing of these transits if there was something else we don't see, something would actually influence the timing of the transits?
I'll go into all that.
Yeah. Dan Fabrici is going to talk all about transit timing, I'm sure. No, it is the one that has done the most transiting planets, but there are a lot of ground-based surveys. I think I took it out. I actually had a slide at one point where for each method I summarized the current projects and future projects. But there are a bunch of ground-based surveys. Like when I was a grad student, I worked on one at UNSW. Kepler and Corot were past spacecraft that did transit surveys. Next year, there's a NASA mission called TESS, which is launching, which is going to do another transit survey of the whole sky. Kepler did a little patch of the sky, and TESS is going to do the whole sky. And there is KELT, the kilo degree extremely little telescope. KELT is a ground-based survey that's found 20-some transiting planets so far and continues to pump out really exciting discoveries. So there are many. And the reason is because as I was saying, this 1% photometry is actually accessible from the ground. If you have a smallish telescope, like 10, 15, 20 centimeters, you can see these from the ground. So this is even amateur astronomers are getting into the transit game for Jupiter-sized things. Earth-sized things are much, much shallower, and the photometry, the quality of the photometry that you need is much, much higher. So you can do hot Jupiter stuff from the ground, and lots of people are doing it. I worked on Kepler, so if the talk comes across a little Kepler strong, you have to try and take out my Kepler bias.
And just wondering about the 8 planets in total. Do we know what kind of planets they are? So they what Jupiters?
So they're actually a mix. The one that's at the longest period, the 330 days, is a Jupiter-sized thing, which is just, for that star, is probably just on the inner edge of the habitable zone. So if it had rocky moons, they could potentially be habitable. The inner planets are Earths and super Earths, rocky sorts of things. So it's almost a solar system analog in the sense there's small inner things and big outer things, but it's all just kind of scaled in a bit. Everything's kind of brought in closer, given that the Jupiter-sized thing is where Earth is and everything's shoved in. Okay, so you can get the size of the planet from the depth of the transit.
So this star.
No, this is good. This is good.
Yeah, so that depends on the size of the star. So our sun is a middle-sized star, right? So if this star is smaller than our sun, then the relative notion of sizes is not like what Jupiter, right?
Yes, so this is a really good point. The star that the 8 planets are around is actually the same size as our star. It's a G0 star. So these planets are all way too hot. But this is something that was talked about a lot 10 years ago and has really become the craze now. If you look for planets around M dwarfs, so M dwarfs are a tenth to half the size of our sun, then this relative dip becomes much larger because if you put an Earth-sized thing around a sun-like star, the depth is 100 parts per million. But if you put an Earth-sized thing around an M dwarf, it's only 1%. And I was just saying, 1% you could do from the ground. The problem with M dwarfs is that they're all quite faint. They're everywhere, but they're all quite faint. So it's harder to do an M dwarf survey. But there is a ground-based survey called MERF, M-Earth, which is looking for Earth-sized things around M dwarfs and has found 2 or 3 at this point. All right. Okay. No, this is good. Ask questions. It's pedagogical. You want to learn stuff. The other thing a transit can tell you from the very specific shape of the transit, so where it starts, where it turns over, the shape of the bottom, you can actually constrain several other aspects of the system, including the semi-major axis. If you know the stellar radius, you can get the impact parameter, which is why I wanted a whiteboard. So the impact parameter basically tells you where on the star's limb the transit is happening. So in the animation that I showed, you had Mercury going across the top. So Mercury had a very high impact parameter, and you had Earth going across the middle. So this would be an impact parameter of 0, and this would be like 0.8. So the impact parameter tells you where on the star it's crossing, and that changes the shape of this. So if you have very flat bottoms, you're going across the middle of the star, the more V-shaped it is, the more you're getting close to the edge of the star. So if you have very precise photometry, you can start to learn more things about the orbit of the star than just the size and the period. Okay, the challenges for doing transit survey. One of the things I wanted to touch on was the fact that, the idea, the platonic ideal of an exoplanet transit is this beautiful U-shaped thing. But you never see that in reality because there's a whole bunch of other mess that's happening at the same time. So I alluded to the fact that the star is doing stuff. If you have a spacecraft or a ground-based instrument, you're getting systematics from your instrument. Your detector is adding photon noise. So at the end, you're dealing with something that doesn't look like a transit anymore. And one of the things you have to deal with, and what has been a real big leap in the field in the last 15 years since I was a grad student, is dealing with this, is modeling this out, using more and more sophisticated statistical processes to take out these noise sources and bring you back to this beautiful platonic ideal of a transit. So this is something that people have been working on a lot, and is a very exciting, development in the field. Okay, so let's talk about how you would go about finding transiting planets. There's really 2 different types of transit survey you can do. One is a wide, shallow survey, and one is a narrow, deep survey. So as I said, you need to look at a lot of stars to find transiting planets because most of them don't transit. So you just have to increase as much as you can the number of stars you can look at. And you can either look at the whole sky, but very shallow, not very deep. You're not looking at stars very far away. You're looking at all the nearby bright stars. Or you can concentrate on one section of the sky and just drill deep, get all of the faint stars and have a lot of sky. And each of these strategies has different pros and cons. The wide shallow survey is the sort of thing that's being done by the ground because you can't get very deep from the ground with a smallish telescope. But you can do bright stars from the ground with a small telescope. So that's what people are doing. This is the sort of thing that amateurs are getting involved in, these wide shallow surveys. If you want to go deep, you need a bigger telescope, and that's going to cost you more money. So that's why this is the technique Kepler used. Kepler did this narrow, deep survey. If you're targeting bright stars, there actually aren't that many bright stars in the sky. You have to look at larger and larger sections of the sky to see them. So that's why you need a wide field of view. And because you're usually doing this from the ground, you have the stupid sun that comes up every day and stops you from being able to look at your planets. So you basically, and also the Earth is moving around, so that patch of sky that you want to keep looking at, and then it's not up anymore. So you're usually only looking at these patches of sky from the ground for a few months at a time. And that already, as we talked about, that's going to limit the kind of planet you can find because you need several transits. So if you're only looking at the sky for a few months, you're not finding Earth planets, right? You would have to look at the same patch for years and years to see Earth planets. So you're looking for and finding short period planets around nearby bright stars. Now these are excellent planets to find just because they're not Earth. Everything doesn't have to be Earth, that's okay. These are excellent to find because they're really good to follow up. These planets around nearby stars, you go get your 8-meter time or your 10-meter time, you go and look at them and you measure their masses, you can look at their atmospheres, you put Spitzer on them, you do all sorts of fun stuff. All of the things that you can't do with faraway planets. So Kepler has been a dramatic success, found thousands of planets. They're all useless. They're all useless because they're all far away. They're all thousands of light years away, around 12 and 13 and 14 magnitude stars. So that's great for statistics. That's great for telling us how common planets are. And that's what Kepler was designed to do, find out how common planets are. But if you care about an individual planet, measuring its properties, finding out, drilling down further, the planets are all rubbish. So you need these nearby bright targets to really characterize a planet. So these are all the sorts of ones that are being found by these ground-based surveys at the moment, and in the future will be found from space as well. The other difference between these two types of surveys is if you care about the habitable zone. So like I said, with these ground-based short stare surveys doing wide field of view, you're not sensitive to Earth-like planets. Doesn't mean you're not sensitive to the planets in the habitable zone. It means you're sensitive to planets in the habitable zone of different types of stars. So M dwarfs, the habitable zone is much closer. So around stars like the Sun, D dwarfs, Earth is in the habitable zone 365 days. Around a little M dwarf, the habitable zone is only a few weeks. You think of it like a roaring campfire on the beach. At the start of the night, you have to be quite far away. It's really hot. But as it burns down, it gets cooler. It gets closer. So the habitable zone around these M dwarfs is very close. So you can actually access them from the ground with these stairs that only go for a few months. So you are sensitive to planets in the habitable zone, just not sun-like stars. And we can have a whole different discussion about what habitable zones around other kinds of stars look like, because we don't really know that yet. We're in the process of finding that out. But that is the difference between the two. And here's just a couple of highlights of surveys that are doing wide, shallow searches for planets. So KELT is the ground-based mission that I just talked about. K2 is the successor to the Kepler mission. So Kepler stared at that one patch of sky for 4 years and then broke. But what they found out they were able to do with it is a different kind of survey where they tiled the ecliptic. So they look at little patches of the ecliptic for 80 days at a time. And so they basically converted Kepler from being this narrow deep survey into this wide shallow survey, which is a really incredible reuse of the spacecraft and has been fantastic in terms of discoveries, not just planets, but other science as well. TESS is this mission that's launching next year that I mentioned. And Plato is a European mission that's launching next decade, which is actually going to do both. Plato has two modes. It has a stare mode where it's going to sit for a long period of time on one patch of sky, including where Kepler was. And it has a tile mode as well. So it's actually employing a combination of both, which is going to be very cool for the planets it finds.
How long is a long period of time?
For Plato, a year. So not as long as Kepler.
Oh.
But it is going to stare for a year at the Kepler field again.
Doesn't get you convinced to stare longer? You'd be away.
The consumable is always money.
Does it cost that much to just stare longer? I mean, just a spacecraft up there with a little bit of coolant like that.
Yeah, well, you have to pay all of the people to spend that year downloading the data, processing the data, making it available. It's not just the spacecraft, it's all of the people supporting.
one place you have to pay them to?
Yeah, so that's why I think they went for this combo. But they might do an extended mission. So like Kepler got an extended mission before it broke. Tess is already planning for an extended mission. Plato will probably get an extended mission if the consumables are all.
So Plato's not looking for Earths around G2 stars.
No.
Is there any mission that's going to look
Microlensing missions. We'll get to microlensing. All right, so what is the transit method found so far? So here is a plot showing the period of the planet, and now I'm showing the radius in Earth radii. So Earth is here. So not quite down here. But what you can see is that the transiting method is sensitive to short period things, and that's just because you get so many more transits. And it's sensitive to, and this is all Kepler. Kepler made all of this happen. All of these small, like 1 to 4 Earth radius things. All right, the radial velocity method. This relies on the fact that as a planet's going around a star, the star's not just pulling on the planet, but the planet's pulling on the star as well. So the sun in the middle of our solar system is actually getting pulled around by Jupiter. So if you were an alien civilization looking at the sun, now you don't actually have to be exactly in the plane like you would with the transit method, but you can see the sun moving. And how do you see the sun moving? By looking at the spectral lines, which are getting blue shifted towards you as the star comes towards you and red shifted away from you as the star goes away. Now, this is a plot of basically the speed of a star with time. This is 51K, which is the first one that was found with the radial velocity method. And what you get is this semi-amplitude of the RV curve, K. And K depends on, amongst other things, the mass of the planet. And importantly, you don't get the true mass of the planet, you get a projected mass of the planet along the line of sight. So if the planet's orbit is inclined out of the plane, you're only getting the component of the velocity that's in the direction to you. You can't measure the component out of the plane. So you're sensitive to the mass. So radial velocity gives you the mass. So remember I said before, transit gives you the radius. If you can observe something transiting and then measure its radial velocity, now you have mass and size, and now you can talk about density. All right, here are some examples of the speeds of stars depending on planets. So if you put Jupiter at 0.1 AU, the speed of the star that it induces as a sun-like star is 90 meters per second. But you can see that this really rapidly drops off. And for an Earth in a 1 AU orbit, it's 9 centimeters a second. So we're trying to measure the speed of a star hundreds to thousands of light years away at the speed of a tortoise walking along the ground. So this is really difficult. And this is one of the reasons why radial velocity hasn't been sensitive to Earth-sized planets in Earth-sized orbits around sun-like stars yet, because we haven't managed to achieve this level of precision as yet. We're working on it. There's a bunch of noise sources to beat down. Stars do stuff in radial velocity as well as in photometry. Stars have flares, they have granulation on the surface, they have active regions that flare, they have magnetic cycles, so like the sun has an 11-year magnetic cycle, which changes. Sometimes the sun has lots of sunspots and sometimes the sun doesn't have a lot of sunspots. So this all manifests in radial velocity curves. That nice 51 peg light curve I showed you because it's nice. That doesn't mean it's typical. So what's one of the ways we get around this? I just want to briefly talk about the two main ways that people calibrate their light curves, because the stars are doing all this stuff and other things are doing stuff too. The instrument is doing stuff, the atmosphere is doing stuff. The Earth makes it really hard to find planets. So the two different ways that radial velocity techniques use to calibrate wavelength. The first one, so this is the light from the star. This is your instrument measuring your radial velocity. This is your telescope rather, and this is your detector. So you insert something in the line of your flux, which you know the wavelength of. So the iodine cell, you know what all the wavelengths of the iodine lines are. So you basically get this imprint of a reference grid of spectral lines on top of your stellar spectrum. So when your star is moving back and forth relative to this fixed grid of reference lines, you can measure what the change in the velocity is. The other way people do it is by having two different channels through their telescope, their detector, and through one channel they shine light out of, for instance, a thorium-argon line, and through the other channel they have the starlight. And basically they look at their two detectors and they say anything that's happening to the thorium-argon lines is also happening to the stellar lines, and that's how they calibrate them out that way. So those are the two major ways that people use to calibrate stuff. So what's radial velocity sensitive to? So here's period again. Now I'm back to mass. I'm just making it fun for you. Now I'm back to mass. And the red points are the radial velocity. So you can see we are sensitive to longer period things than transits. Now we're out to a few AU. But we're not sensitive to like Earth-sized things yet. Earth is down here. And that's just the precision. It's just too hard. We're working on it, but at the moment it's too hard. All right, microlensing is magic. I'm just gonna say that because I don't think there's any microlensing people here. Microlensing is what happens when you're looking towards the bulge of the Milky Way and there's just a bajillion stars, right? If you have a star between you and the bulge that's going along, what it can do is bend the light from the stars in the background and it lenses them. And what you see when you're actually measuring the light from the star in the background is it suddenly gets brighter and then goes back again. It's a very characteristic curve. As the star in the foreground goes in front and lenses it. If that star in the foreground has a planet that's in the right place, you end up with this perturbation on your lensing curve. This looks like that. So microlensing surveys are basically long stares at the bulge looking for events that look like this. So far they have found about 50 planets. Here's an example of an actual light curve. So here's this characteristic single lens curve if it was just a single star, and then you see this perturbation caused by a planet.
Perturbations are minutes or?
Hours typically, hours to days. But that's a really important point because microlensing surveys can't monitor every single star with minute cadence. So what they do is they monitor stars. This is a few weeks time scale. They monitor stars once a night and they look for the start of the single lens event. So the single lens event can take weeks to months, but the perturbations due to the planet are much shorter. So what they do is they sit on all of these stars and then they trigger on one. They go, okay, look, there's something happening. And then all of the follow-up networks jump on it. So this is why you can see all the black points. Then suddenly you've got red and green and blue. Everybody jumps on it because something's happening. So now you have better sampling. You know something's happening on this star. So everybody goes and looks at it and then you get the perturbation in good detail. Now where is microlensing sensitive? So remember at radial velocity I said, okay, we're increasing our sensitivity. We're out to a few AU. So now microlensing is out to like 5 to 10 AU. And this is basically just to do with the likelihood that your planet is lined up such that you see the perturbation. It's also sensitive to big things as well as small things, which is nice. This is the only slide I'm going to show about future detections just because microlensing is about to have its windfall. Radial velocity had its decade, transit's having its decade. Microlensing is about to have its decade. Studying versus launching.
Does microlensing have limitations on like the orientation of the system?
So the planet has to be in a special place, basically, in order for it to lens in a detectable way. What you really measure, you don't really measure a mass, you measure a mass ratio between the host star and the planet star. And you don't really measure a period or a distance, you measure a projected period along the line of sight.
What fraction of the time is the planet and the star aligned such that you won't see any planet, even though there is a planet there?
That's a really good question. If you had asked a microlensing person to talk today, they would be able to give you the answer. I don't know. It's not high. That's why they have to look at, you have to look at millions and millions and millions of stars. And it's like 200 million stars to see 100 events a year or something. All right, so direct imaging is basically what it means. If you have the right confluence of circumstances and you can block out enough of the starlight, you can actually see, this is HR 8799, animation by Jason Wang, you can see stars. It's really hard to do this because the contrast ratio between, say, the sun and the Earth is about 1 billion. It's 1 billion times brighter, the sun, than the Earth. So it's really hard to get that contrast ratio down. I'm going to start speeding up. People use either coronography or interferometry. Come ask me about those if you're interested. And people choose to either survey young stars because they're still bright, they're still contracting, they're still hot so you can see them. Or people go to infrared wavelengths where the contrast ratio that I showed gets smaller. And where is direct imaging sensitive? So remember the microlensing detection plot went out to like 20 AU. So now we're at hundreds of AU. So direct imaging is really the one method we have that's sensitive to things that are quite far out that has been successful. All right, astrometry is you can measure the motion of the star actually on the sky that has not found a planet yet, so I'll keep going.
You had it listed as one.
It has one thing that's 28 Jupiter masses plus or minus 2 Jupiter masses. So depends whether you call that a planet. So at the Exoplanet Archive, we have a 30 Jupiter mass cutoff. So 28 just made it, but it's probably rubble.
But it has confirmed it. Discovered somewhere else.
Possibly. The only one I know of is VB10, which was retracted. All right, timing variations are every star basically can act as a clock. And the same way you measure the star moving back and forth with spectral lines, if the star is ticking in some way, you can use that as those ticks arrive sooner or later. So that's pulsars and eclipsing timing variations. And Dan's going to talk more about transit timing variations. And finally, orbital brightness modulations. You can use the fact that the star is reflecting different amounts of light over its orbit to measure planets that way. Here are 2 examples of planets that don't transit but do reflect enough light that you see them. So this is the final slide, so I'll just put it up. In summary, these are some of the techniques I talked about. From each technique, you can measure different things, typically different quantities of the planet. If you can get multiple techniques, that gives you a really clear picture of the planet. Some of them are more useful than others, and this is basically, this is an important point this morning that Mike and Trevor were talking about, is that really, I didn't really touch on, but planets forming outside the snow line. The transit technique is not sensitive to things forming outside the snow line, and that's where we think most things form. So having these other techniques which are sensitive to things outside the snow line is really useful. All right, thanks.